Hi, so we're going to start with a new chapter now. In this chapter is a critical chapter because the type of elements that we are going to introduce here is called energy stored elements. When we introduce these elements, then there is going to be a big change. What is this change? Is this. Before these elements, the circuits that we examined up to now was the resistive circuits. That means they included dependent sources and the resistors only. For this type of circuits, the mathematical tool that we use was linear algebraic equations. So any resistive circuit, no limit on the elements, no limit of the connection. If the circuit is resistor, then in order to analyze this circuit, we've got to use linear algebraic equations to any of them. Or we could use mesh current method or the node voltage method, find all the elements, current and voltages. Now when we introduce these new elements now, the mathematical model that we are going to use is not algebraic equations anymore, but they are differential equations. Therefore, I said this is a critical point and there is a big change. So we are going to see why we use differential equation instead of algebraic equations. Why need that? Why do we need that? So we're going to see these details in here as well. So we said, energy storage elements, the basic ones are the inductors and the capacitors and the mutual inductors. So we are going to see all these elements. The first video is related with the inductance. Inductor is the name of the element. Inductance is the parameter of this element. So let's go inside. Inductor, the market name of this element is coil. Coil is a well-known name. Everybody on the street, they know what coil is, but they might not know what the inductor is. It is composed of coil of wire wound around a core. Charge in motion, which is current, induces magnetic field. The current passing through that coil introduces a magnetic field around it. This element stores energy due to the initial condition. I will explain what that initial condition is in the definition relation of this element. It is a linear element and it is also a passive element. So we are going to see this element, why it is linear, why it is passive as well. So let's see how this element is seen in the market. So this is a simple coil here, which is an inductor element. This is, you could see the coil for this inductor, but you cannot see the coil inside. It is inside of this, so you can't see it by eye. So the size of this element is not that big, so it is in the range of 1 centimeter length. So it is a small element we are talking about. But for the high power elements, these are electronic elements. In electronics, the power range is very low. When the power range goes up, so electric circuits comes in. So in electronics, the inductors that we're going to use is going to be that small size ones, and the inductance L is in the range of millihenry. What is this L? Let's come to the definition relation of this element. Now in here, as we said already, we are going to deal with ideal elements in circuit theory, because we know all the elements which is available in the market can be represented by ideal circuit elements. So that's why it's critical. So why do we need those? I already explained, but I would like to repeat it. These ideal elements, mathematical representation is simple as possible. That's why we are using these ideal elements. So the market element is going to be the composition of these ideal elements. So we show this ideal element inductor like that. And when we are talking about an element, there's going to be two electrical quantities related to this element, which is one of them is voltage, the other one is the current. And in order to measure these quantities, we've got to give references. On the other hand, we know that these references should be given according to passive sign convention. So this is a passive sign convention related references for this inductor. Under this passive sign convention, the definition relation of this element is this. If you look at this definition relation, so the current is this inductor current, and this voltage here is also this element current. So it is very like the resistor definition relation, because in the resistors definition relation, the same element current and voltages are seen in the definition relation. Once again, for this inductor, the same element current and voltages are seen in the definition relation. So what this definition relation says, whatever the current of an inductor, get the derivative of it, multiply with that L value, you get the voltage of this element. So what is this L? This L is called inductance. So inductance has a dimension. So this dimension, the unit of this dimension is Henry. The range of the inductor's inductance values is in the millihenry range. So it's not that big. It's not common 10 Henry inductor element in electronics. But in circuit theory, we could give any value to this. But what is special with that L is, this L represents the physical structure and the chemical material from which this element has been produced. Therefore, this L value is a positive real number. It won't be a negative L value. So that's the definition relation. So conclusion is this. This mathematical model represents this element in practice. How it represents it. So if you apply a current to this, you can observe the voltage that you're going to observe. Assume that there is an independent current source is connected to that inductor, so that means this current source current is going to be equal to the inductor's current. So you're going to get the derivative of this current multiplied with the L. What you get is the voltage. So if you measure the voltage of this element, you're going to get the same result that you get from this equation or from this definition relation. So definition relation tells the behavior or description of the inductor. So another way of saying the same definition relation, how you can get the current of this element in terms of the voltage of this element, then you need integral. This is the inverse operation of the derivative. So if you get the integral of the voltage, so you're going, this is a boundary for the integral 0 to t. So if you replace t with 0, this integral becomes 0 to 0. That means this becomes 0, t equals to 0, IL0 equal to IL0. That value has a special name. So it is written in Turkish here, but it is initial condition, it is called. So from the mathematics, a quantity comes here, and there is a practical correspondence to that value. that is called initial condition, and this initial condition is the source of energy storage. So we are going to see it later on. So we are saying this is the definition. You can use this one as a definition relation as well. Why we call this definition relation? Maybe it needs a bit explanation. Maybe I already said it for the resistors, but I can repeat it for the inductor as well. What is it? Behavioral, let's say how you can check the behavior of human. Let's say Ahmed. How I'm going to check this is the Ahmed's behavior. So an action, if you do an action towards Ahmed, the response of Ahmed is the behavior of Ahmed. So if you kick Ahmed, for example, his response, Ahmed's response to that kick could be another kick. So that's Ahmed. If it is Mehmet, for example, when you kick Mehmet, his response could be, why you kicked me? So an explanation rather than kicking. So different behavior. So that means behavior of any subject can be checked, put an effect on it, and observe the response. So that is the behavior of the thing that you are dealing with. So it is true for the inductor as well. So we're going to apply a current, observe the voltage as the response, or we are going to apply voltage and observe the current as the response. That's why mathematical model here represents that behavior. We already know that if the current and voltage of an element is known, multiplication of those two quantities gives the power of this element. So power of the element, integral of the power gives the energy. If you do this integral calculation, you end up with that result. So that means the energy is equal 1 over 2 L times IL square. What does this mean? This function is always positive. This function, that energy, is function of t. That IL is the function of t. So the result tells me here that energy here is positive for any t value. By definition, this element is a passive element. For any t value, that energy is always positive. That's why it is a passive element. So inductor is a passive element. We've just proved that. So this element, on the other hand, this element is a passive element. We've just proved it, and it is also a linear element. Why it is a linear element? Because the derivative in the definition of this element, derivative operation is a linear operation. Why it is? You can easily remember that derivative of the summation of two functions is equal each function's derivative's summation. So that is the definition of linearity, isn't it? So therefore, since the derivative is a linear operation and derivative is in the definition relation of this element, so this element is a linear element. So it is a passive element and at the same time a linear element. It is not non-linear element, but the linear element. So in here, I'm just reading here and then explaining it. There won't be an instantaneous change in inductance. Instantaneous change means not continuous, it is jumping. Immediate change or instantaneous change, that is, inductance current. So it says there won't be an instantaneous change in the inductor current. Why is that? So you could see it. In here, inductor currents, there won't be inductor current change means, use the mathematics now. If you have a function which has a discontinuity at a moment, let's say, So derivative of this function is going to give you the tangent slope. If there is uncertainty or the discontinuity or an instantaneous change for a specific time, so you cannot define that derivative because the point is not, you don't know where this point is. So uncertainty in mathematics means no corresponding physical quantity. Therefore, we are saying inductor currents do not have any discontinuity or instantaneous change or instantaneous jump. So we could see it in mathematics as well, in the definition relation. But we cannot say the same thing for the voltage of this element. Why is that? Because when you come to the voltage, the operation that you're going to apply to this function, that voltage, is integral. If the function has got an instantaneous change or discontinuity, so this operation tells me the summation, finding the area underneath that curve. So if there is a discontinuity, before the discontinuity you can calculate the area. After the discontinuity you can calculate the area. When you add them up you can find the final area underneath the curve. So there won't be any problem in mathematics and won't be any problem in practice. That means inductor's voltage might change instantaneously, but not the current. In here it says inductor could be considered as an element which yields the derivative voltage of a function along computers before the digital ones is what like that. So what is explained here, if you look at just by the definition relation, if you have a function and try to find a derivative of it, how are you going to do this? This is a mathematical operation. You could do the calculation and then figure that out. But how you could do it in practice, you could use this inductor element to do that. Because if you apply this current as any function, that the function that of which derivative that you're going to get. So if you apply this function as an independent current source to this inductor, the voltage that you're going to measure is going to be the derivative of this function. Therefore, we can say that inductor element gets the derivative of the current passing through it. So in old days, these elements were used for the analog computers. That means before the digital ones. So it was the computer was the analog computers. Analog computers was using these elements. So we just explained the what is ideal inductor and definition relation of the inductor. Next, we are going to see the behavior of this inductor for different effects that you're going to apply to it and see the response. So if you come to this now, this frame, so there is an inductor here of which inductance is 0.5 Henry and an independent current source is applied to this element. So that means independent current source current is equal to this inductor current. Why is that? If you write the Kirchhoff current law equation for this node, so this current is equal to this current. So this independent current source is not a common current source available in the market, but you can design anything like that. In practice, maybe an electronic circuit, but so this is very specific circuit it would be, not general. But mathematically we could use it anyhow. So if you draw this function, which is of the function of t, here is this ILT change, inductor current. So get the derivative of it and multiply it with L. That's the definition relation. Here you are. Then you're going to end up with this curve. So if you look at this curve, what the difference between these two, You see, this all the values here for any t is positive here. But in here, it becomes negative. The 0 is here, but not this 0 is here. This is 0 is here. And this voltage becomes negative here, but not the current. So multiplication of the current and the voltage gives you the power. Since this area is negative, so you're going to see a negative power here. Negative power, we said if an element current is negative, then it delivers power. If it is positive, then it absorbs power, we said. We've got to pay attention right here, because the energy delivered here is not the energy delivered by this element. Why is that? Because before this negative power, we have a positive power here. So the energy delivered in here is the one already being absorbed in this time interval. That energy comes from the independent current source. So this power here, that positive power here, coming from that active element, which is the independent current source. So that means this element gets the power or the energy from this element in this time at the beginning, stores that energy and gives it back this energy, the energy that it is absorbed from the independent source. It is not this element energy, but this independent source energy given back. That's why we call these elements are energy stored elements. So if you go to the title here, energy stored elements, that's the reason why it is energy stored element. If it was at the beginning, there was a negative power here at the beginning. If there was a negative power, then it becomes a active element, so it is not an element like that, it becomes an independent source type of element or dependent source type of element. So if this is inductor's power, pay attention, we are talking about the power curve here. So if you take the integral of that power, you're going to end up with this. In there, for any t, this energy is positive. That fits the definition relation of the passive elements. So conclusion is this: energy is positive for every t, then this element is called passive element, and this inductor is a passive element for this specific case as well. So another examination of the inductor element. This time we applied an independent voltage source. This voltage source has got a pulse. So that you can draw the rest of it after t equal to 1. The value of this voltage is equal to 0. Not seen here, but you can think it like that. So this curve here is a pulse, just one pulse. So if it is voltage, so we're going to, in order to find the current, so this is independent voltage source, this voltage source voltage is equal to this inductor's voltage. So you're going to get the integral of it. Integral of this gives you that red curve, and multiplication of those two gives you the power change, and the integral of that power gives you that red one. So after t equal to 1, it becomes 0. Why is that? Because one of the quantity is 0. Multiplication of with the other quantity gives you 0, isn't it? So after t equal to 1, there is no power absorbed by this element. So you can easily see that in this case, in any case, but also in this case, that the power, that means the area underneath that curve, is always positive. That means for every t, the energy value is positive. So those two frames tells us, just give you two examples that this element is a passive element. There was a note here that I was taking a video until 3 o'clock. So after 3 o'clock, yeah. The next frame is related with the serial inductors. If there are many inductors are connected in serial like that, there is an equivalent inductor element which does the same job with these serially connected 3 elements. What does this mean? It means if you replace those 3 serially connected inductor with only one inductor of which inductance is equal to summation of those, then the voltage and current that you're going to observe in the first one and